We will be covering the quiz for practice solutions. So let's start with number 1. The question is, how much work is performed by a constant force, 8 I hat minus 3 j hat newtons, acting on an object which is displaced in a straight line by 10 I hat plus 4 j hat m? And the answer is in joules. Okay, this is a straightforward application of the work done by a constant force. F is F dot d, where d is the displacement. The force has components 8 and minus 3, so I'll write it this way. And the displacement is 10, 4. The dot product, F dot d, what you do is you multiply the x components together. Then you multiply the y components together. And then you add the x product and the y product. So 8 times 10 plus negative 3 times 4. So you get 80 minus 12 is 68 joules. Okay, moving on to number 2. A block of mass 3.30 kilograms moves in a straight line on a frictionless horizontal surface under the influence of a force that varies with position as shown in the figure. How much work is done by the force as the block moves from the origin to 8 meters, from here to there? So we have force and we have position. So it's all along a straight line. Okay, so the work done by a varying force, a non-constant force, is the integral from the initial x to the final x of fx dx. Okay, that's the generalization of f dot d. If it's a non-constant force, you have to do the integral of f with respect to x. Okay, so we need the area under the curve. This portion here will be positive, this portion here will be negative. So we have to locate, it's important to locate where it crosses here. We don't need the exact point, but if I read off the graph, it's about 6.8. Okay. Now we just need the area under this part here, the positive part, and then subtract the area of this triangle here. Okay, let's break it up to regions. We first have a rectangle. Okay, this is region 1. And region 1 has a height of 4 newtons, a width of 2, 2. So the area is 4 times 2 equals 8. Region 2 has, okay, it's a trapezoid region. You can either take the rectangle underneath plus the area of the triangle, or you can use the fact that a trapezoid, where I have the dimensions 4 here, 7 here, and this width here is 2. Basically, for the trapezoid, you just average the two unequal sides, the opposite sides that are unequal, 4 plus 7 divided by 2, and multiply by the other dimension, 2. And so that comes up to 11. If you don't remember the trapezoid area, all you need to do is just break this apart into triangles and rectangles, and you can get the answer that way. Okay, for number 3, we have another rectangle. The width is 2, the height is 7. Okay, that's just read off from the graph. 7 times 2 is 14. 7 times 2 is 14. Region 4 is this triangle. So the width is from 6 to 6.8. So that's 0.8 in width. Okay, and the height is 7. So it's 1/2 times 7 times 0.8. And that comes out to 2.8 joules. Now the last part is this triangle here, okay? But the area, because the height of the triangle is negative this time, I have 1/2 negative 10, okay? And the width is 1.2. I get that from going from 6.8 to 8, that's width of 1.2. 1/2 times negative 10 times 1.2 is negative 6 joules. So the total area is 8 plus 11 plus 14 plus 2.8 minus 6.0. And that comes out to 30 joules. Okay, Moving on to number 3. A block with weight 520 newtons is pulled up at a constant speed on a very smooth ramp by constant force. The angle of the ramp with respect to the horizontal is theta equals 16 degrees, 16.2 degrees, and the length of the ramp is 12.1 meters. They want to know the work done by the force of pulling the block all the way up to the top of the ramp. Okay, well, you can do this problem several ways. You can do this problem, you can try to figure out, well, they don't actually tell you exactly at which angle the force is pointing. So what that tells you, you can always assume that the problem is well written. What that tells you is that the angle doesn't matter. So what you could do is you could just then assume, take the example where the force is just pointing straight up the ramp, and then figure out how big that force needs to be in order for it to go up with constant speed. So the net force needs to be 0. Remember, constant speed means the acceleration is 0. So you could figure out, if we had a force going straight up the ramp like this, how big it needs to be. Then we could do F dot D and calculate the work done. Okay, that's one way to do it, but that's sort of an ugly way of doing the problem. It's one way of doing it. A simpler way of doing it is just saying that this force is an external force. It's not a conservative force. It's not like gravity or a spring force. So let's just treat it like we do non-conservative forces. It's some external outside force. Okay, so we have the work done by this force, this non-conservative force, is the change in the mechanical energy. In other words, delta K plus delta E, the change in the potential plus the change in the change in the kinetic energy K plus the change in the potential energy U. Okay, so we have K final minus K initial, that's delta K. And then for delta U, we have U final minus U initial. But it's a constant speed, so whatever we have for the initial kinetic energy is what we get for the final kinetic energy, so this is 0. Now for the difference in the potential energies, that's just the potential energy for gravity, so it's mgy final minus mgy initial. Okay. At this point, we just have to calculate the height, the initial height. All right, let's take y equals to 0 to be the bottom. You could take it to be the top. It won't matter because we're going to take the difference between the potential energies, and the reference height won't matter. But we'll take it to be the bottom. I suspect most of you want y equals to 0 to be the bottom. Then this height here will be this side of this triangle. We have this triangle has an angle of theta. It has a hypotenuse of 12.1 meters. So then this side here, the sine is the opposite over the hypotenuse. So we have 12.1, the hypotenuse, times the sine of 16.2, the angle, and that comes up to 3.38 meters. Okay, so now we have that y final is equal to 3.38 meters, and so the change in the UF minus UI is going to be mg y final, y initial 0, so that just drops out. And we have mg y final, but they actually don't give us the mass, they give us the weight of the block. So they already take into account m times g, the weight. So that's the weight here, W. So m times g is the weight. So I can write this as the weight times y final. So we have the weight 520 times the y final, which is 3.38, and we get 1,760 joules. Okay, let's go on to number 4. A 65 kilogram diver is a height 1.1 meters above the water, falling with a velocity 8.50 meters per second. Calculate her kinetic energy as she hits the water. Okay, so we have this diver. We can say, okay, so let's take this line as to be y equals to 0. The diver is upside down, coming in. Okay, and so as I said, the water surface will take as y equals to 0, and we're going to use conservation of energy, mechanical energy. K initial plus U initial is equal to K final plus U final. Okay, so the diver has some speed that we're told is 8.5 meters per second. Okay, and this diver, she is a distance of uh, 1.1 meters above the water surface. Okay, that's what we know. So the initial kinetic energy is 1/2, and oh, I forgot to tell you, her weight, or sorry, her mass is 65 kilograms. So to get her initial kinetic energy is 1/2 mv squared, mv initial squared, or 1/2 65 times 8.5 squared, and that comes out to 2,350. And then U initial is the mass of the diver, which is 65 times 9.8 g times Y initial, that's 1.10. And so we get 701 joules. Now, the final kinetic energy is actually what we want. U final is equal to 0 because we took this to be the final height to be 0. Okay. And so U final equals 0. Now we can plug in everything. We have that K initial plus U initial equals K final plus U final, conservation of energy, mechanical energy. So we get K initial is 2,350. We get that U initial is 701. And then this U final was 0, so we just get K final. So we get K final is equal to the sum of these, it's 3,051 joules. Okay, the next problem. A car accelerates uniformly from rest up an inclined road which is rising uniformly to a height of h, which is 48 meters. Find the average power the engine must deliver to reach a speed of 26.1 meters per second at the top of the hill in 17.3 seconds. Okay, so let's try to dissect this. They want power, but in order to get power, they give us time, so we need to figure out work. So the first step is to figure out how much work does this engine deliver. Okay, this engine is not gravity or a spring, so we're going to do this using treating it as a non-conservative force, because it is. The work done, the engine is delivering a non-conservative force, so it's doing work NC, WNC, for non-conservative force. That's equal to the change in the mechanical energy. The mechanical energy is kinetic plus potential, so we have the change in kinetic plus change in potential. All right. So now, the initial kinetic energy, it starts from rest. That's what's given in the problem. Okay. So K initial is equal to 0. K final, that's the, we want to know, so the final is at the top of the hill. So we have 1/2 mv final squared. We're told the mass of the car is 600 kilograms. The final speed is 26.1. So we get 1/2 times 600 times 26.1 squared. And that's 2.04 times 10 to the 5th joules. Okay, now the initial potential energy. So initial potential energy, we take, let's say, y equals 0 at the bottom, so then ui will be equal to 0. Now uf will be mg times y final, okay, right here, y final. Now y final is given as 48 meters, so we have 600 as the mass, times g 9.8 times 48. Okay. Now we have multiplying these together, 2.82 times 10 to the 5th joules. Okay. Now, the work done by the non-conservative force, or this engine, will be the change in the kinetic energy plus a change in the potential energy. Remember, that's a change in the total mechanical energy. So we have K final minus K initial plus U final minus U initial. So we have K final is 2.04 times 10 to the 5th. K initial 0. U final is 2.82 times 10 to the 5th. And the U initial 0. So we add these together and we get 4.86 times 10 to the 5th joules. To get the power, the average power, we take the work done, 4.86 times 10 to the 5th, and just divide by the time, delta t. That's 17.3 seconds. That's given in the problem. And so we get 2.81 times 10 to the fourth watts. Okay, let's go on. Number 6, a moving 3.30 kilogram block collides with a horizontal spring whose spring constant is 370 newtons per meter. The block compresses the spring a maximum distance of 7.50 centimeters from its rest position. The coefficient of kinetic friction between the block and the horizontal surface is 0.410. The question is, what is the work done by the spring in bringing the block to rest? Okay. Now, the spring is a conservative force, so there's many ways to do this problem, but let's just use the fact that it's a conservative force, and so the work done by the spring is negative the change in the potential energy of the spring. Okay, that's a fast way to get the answer. You might be able to get it just as fast a different way, but this will work. So we have negative the change, that's final minus initial, U final minus U initial. So the potential energy for a spring is 1/2 the spring constant K times the deviation away from equilibrium, x final squared, minus 1/2 K x initial squared. Okay, it starts from equilibrium, the spring starts from equilibrium, so this is 0. So we just need minus 1/2, 370, that's the spring constant, times the deviation from equilibrium, how much it's compressed or stretched, 0.075, because this was in centimeters, 0.075 squared. And that comes out to negative 1.04 joules. Number 7, how much mechanical energy is being dissipated by the force of friction while the block is being brought to rest by the spring? Okay, in this problem they've given us quite a lot of information, so we can get this answer from the work energy principle or just directly calculating the work that friction is doing. I suspect most of you will probably just do a direct calculation of the work done by friction because that's maybe more straightforward. Okay, so let's do it that way. If you want, as a secondary exercise, you can try to use the work energy principle. I'll talk about that after we cover this solution. Okay, so we have the normal force going up. We have gravity going down. They must cancel each other because those are the only vertical forces, and there's no acceleration in the vertical direction. F net y is equal to 0, so the normal force equals Fg. Okay, so that's m times g. 3.30 is the mass, and g is 9.80, so we get 32.3 newtons. Now, we have then the spring force, and we have the force of kinetic friction. Okay, so the block is moving in this direction, so the kinetic friction is going in the opposite direction. So the force of kinetic friction is mu k, is coefficient of kinetic friction times the normal force. We got the normal force to be 32.3 newtons, so we get coefficient, which is 0.41 times 32.3, and that's 13.3 newtons. So now we have 13.3 newtons going in this direction, and we have the displacement going in this direction, and so that displacement is 0.075 meters. Right? And so now the work done by friction is Fk times d times the cosine of the angle between these two vectors, which is 180 degrees, or just you get a minus 1. You could have guessed the minus 1 just by the fact they're going in opposite directions. So we get minus Fk times d, and the force of kinetic friction we said was 13.3, so we get minus 13.3 times the distance 0.075, and that comes out to minus 1.0 joules. So 1.00 joules is the energy that's dissipated, that's lost. Okay, let's go on. This one is perhaps the most tricky problem of the practice quiz. Let's go through the steps. All the steps are rather straightforward. Maybe the last part of it is a bit complicated. Okay, how to deal with this percentage issue. So let's look at it. We have a 40,000 kilogram railroad freight car that collides with a stationary caboose car. They couple together, they stick together, and 12% of the initial kinetic energy is dissipated as heat, sound, vibrations, and so on. What is the mass of the caboose? Okay, let's first set up the collision. We have a 40,000 kilogram freight car moving with some speed v. Okay, they don't tell us v. That might bother you, but the what that means is it doesn't matter. Okay? And by the way, if you have a situation where they don't tell you some variable, and you can assume that the problem doesn't have a mistake, assume that we know what we're doing, writing these problems. And so if they don't tell you a variable, very often, pretty much in all cases, it doesn't matter what that variable is. You can, so ideally you should just carry that variable through and check that it cancels out. But if you find that sufficiently annoying, then you can actually just set that to 1. So if you don't like carrying things out, you can just say v equals to 1 because it doesn't seem to matter in this problem. And that generally works. Okay. So now let's look at the initial case. We have 40,000 kilograms with some velocity v. This caboose has mass capital M. It's not moving. And so now we have, there's a missing 0 here. We have 40,000 plus m mass here, and that's moving with the velocity v final. So now we have conservation of momentum. We have 40,000 v plus 0, that's m times v, plus m times 0, so that's 0 here. And then we have 40,000 plus m times v final. Okay, so this is the initial total momentum, and this is the final total momentum. Okay. Now let's solve for the final velocity. Final velocity is 40,000 v divided by 40,000 plus m. Okay. Now we have this information about 12% of the initial kinetic energy is lost. Okay, so let's look at the kinetic energies. So the initial kinetic energy is 1/2 times the mass times the velocity initial squared. So 1/2 m 40,000 v squared. Then the final kinetic energy is 1/2 40,000 plus m is the mass times the velocity final squared. Okay, but we solved for this final velocity. That's why we did the work. So we have 1/2 40,000 plus m times the final velocity, this guy, squared. Let's try to simplify a little bit so we don't have to do quite so much work. The 40,000 plus m in the numerator cancels one of the factors in the denominator. We still have 40,000 squared in the numerator. The 1/2 is here. And we have v squared and one factor of 40,000 plus m in the denominator. Now, they say that the final kinetic energy is 12% less than the there's a reduction of 12% of the initial kinetic energy. So the way I interpret that is 100% minus 12%, okay, times kinetic initial is equal to the final. So the final is reduced by 12% compared to the initial. Okay. So 100 minus 12 is 88. 88% is 0.88. So we get the K final as 0.88 kinetic initial. Okay, so there's a reduction of 12%, so I say 100 minus 12 times the initial is equal to the final, and I convert these into decimals. So from percentage to decimals, you just divide by 100. So we have that K final divided by K initial. This, by the way, this part may be the tricky part here, getting this to work out. So K final over K initial is 0.88, but we already had this expression for K final and this expression for K initial, so let's just take the ratio of the two. This is K final, this is K initial, from here and from here. So simplifying a bit, we can cancel one of the factors of 40,000, and then we can also take this guy and put in the denominator here. The 1/2's cancel, the v squares cancel, so as we expected, the v's don't matter. So now we have this thing must be equal to 0.88. And so we have that m must be equal to, okay, just solving for m here, we have 40,000 minus 0.88 times 40,000 divided by this 0.88, you get 5,450 kilograms. Okay, moving on to number 9. You push a box which subsequently slides over a table with a coefficient of friction uk is equal to 0.22. What initial speed does the box need in order to slide a distance of 1 meter? Okay, so we're asking what is the small speed needed to go a distance of 1 meter, so we're going to make it so that the initial speed is such that it stops at after 1 meters. Okay? So the idea is we have kinetic friction. We can calculate after 1 meter how much work the kinetic friction will do. Again, the mass of the box is not given, so apparently it doesn't matter. So you can, if you don't want to carry the capital M around, you can just set it to 1. Okay, that's perfectly fine. All right, we have normal force going up. We have gravity going down, mg. Because there's no acceleration in the vertical direction, Fn is equal to Fg, and that's equal to m times g. Now the force's kinetic friction is mu k, the coefficient of kinetic friction, times Fn. So that's mu k times m times g. So g is 9.8. Mu k is equal to 0.22, and I realize I shouldn't have the minus sign appearing here quite yet. Okay, sorry about that. I'll fix it in the notes. Now, then we can apply the work-energy principle. So we have the net work done by all forces equals change in the kinetic energy. Okay, you could also use the work done by conservative, non-conservative force is equal to the change in the mechanical energy. Then you have an extra plus delta U here, but there's no potential energy in this problem because everything's horizontal, just sliding over a table. I guess technically it should have said that to be it should have said horizontal table, but it's assumed. Yeah. Okay, so now we have the net work done, so we're talking about friction. Okay, the vertical forces don't do anything. So Fk goes this direction, and the displacement is in this direction, and d is equal to 1 meter. So the net force done is minus Fk times d, and so that's it's 1 times the force, 2.16 m, and putting a minus sign in. So the change in the kinetic energy is the work done by the net force, and so we get minus 2.16. Okay, so now we have the change in the kinetic energy. Now, if we say that the box will stop after 1 meter, then K final is equal to 0. That means then the initial had to be 2.16 in order for the change to be negative 2.16. So we get 1/2 mv initial squared is equal to 2.16 m, and the m's drop out here, and so we get v initial is equal to 2.08 meters per second. Again, if you wanted to just set m equals to 1, that would have worked just fine. You would have gotten 1/2 vi squared is equal to 2.16 at this stage. Okay, let's go on. On a roller coaster, the total mass of the cart with passengers included is 275 kilograms. At this peak here, K, that we'll take that as initial, is 49 meters above the ground. The peak here, which we'll take as final, is 21.5 meters. At K, the speed is 15.2 meters per second. At L, the speed is 13.7 meters per second. And the cart stays on the rails. The question is, how much energy is lost due to friction between the two peaks? Okay, we just need to calculate. We just basically are going to use that the work done by non-conservative force is delta K plus delta U. Okay, that's the work done by friction. So we need all the energies. So the K at the initial point, at point K, okay, the kinetic energy initial is 1/2 mv initial squared. So the mass is 275. The v initial is, we're told, is equal to 15.2 meters per second. So 1/2 275, 15.2 squared is 3.16 times 10 to the 4th joules. The initial potential energy, the height is 49 meters, so the mg times y initial, so the mass is 275 times 9.8 times 49, and we get 1.32 times 10 to the 5th joules. Now at the final point here, the final speed we're told is 13.7, and so we get 1/2 times 275, the mass, times 13.7 squared, and we get 2.58 times 10 to the 4th joules. The final potential energy is m times g times y final. This is at a height of 21.5 meters, so we have M, which is 275 times 9.8 times 21.5, that comes out to 5.79 times 10 to the 4th joules. Then we say the work done by a non-conserving force is a change in the kinetic energy plus a change in the potential energy. Okay. And so K final minus K initial plus U final minus U initial. Now we just plug in the values. For K final, we have 2.58 times 10 to the 4th. K initial, we said was 3.14 times 10 to the 4th. Then U final, we have 5.79 times 10 to the 4th. U initial, we have 1.3 times 10 to the 5th. Putting that together, we get negative 8.01 times 10 to the 4th joules.